Hey everyone. So today what we're talking about is Maxwell Boltzmann distribution. Maxwell and Boltzmann were two separate scientists. They decided, kind of on the same conclusion without ever meeting each other, that gases tend to spread their speeds differently based on their size or based on the temperature. And you'll see what I'm talking about here in a second. But we're just going to be able to analyze Maxwell Boltzmann distributions graphs, which actually is pretty simple. So, say we have two containers here, and they have the same number of gas molecules. So let's just say helium, right? We got 10, 1, 2, 3, 4, 5, 6, 7, 8. We got 10 helium molecules in here, or atoms in gas form, and we'll have the same over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then let's just say that this guy is at 200 Kelvin and this guy is at 400 Kelvin. Okay? It is good to know that all these gases won't be traveling at the same speed. Yes, on average, this 400 Kelvin one, the molecules are going to be traveling faster, but some will be traveling really fast. There will be one in there that travels kind of slow. Right? If you imagine all these people bumping into each other, some of them will be bumping in and slow each other down after they bump into one another. So when you look at this, you might get some gas molecules moving fast, some moving slow, but overall they are moving at an average kinetic speed based on their temperature. So this one might have larger arrows, but there will be ones that move not so much. On average, the arrows will be larger, but again, it doesn't mean that all of them have to be the same speed. So anyway, what happened is that Maxwell and Boltzmann looked at these speeds and said there's got to be some way to kind of average these speeds out and put them in a visualized sense. Well, that's where they came with their Maxwell Boltzmann distributions. So they have this nice little graph here. Okay, at the bottom, they have speed, and on the left side, they have number of molecules. So there will be a certain number of molecules traveling a certain speed. That first box that we looked at, that was at 200 Kelvin. It'll show a curve that looks something like this. Remember, they both have 10 molecules. It's just saying that there's a good chunk of molecules that are going to be going this lower speed. Yeah, there might be one molecule over here that's going really slow, and there might be one molecule over here that also goes really slow. But that 400 Kelvin curve is going to look something like this. It's going to be flattened out, but there's going to be a lot more molecules traveling at a faster speed, and a lot more traveling in this area at a high speed, and maybe just a few traveling at a lower speed. Okay? So as temperature picks up, that curve flattens out and our average speed becomes further right. So as you can see, our average speed here, yeah, there's a lot of molecules going that speed, but it's a really slow speed. Here there might be less molecules going this speed, but remember there's a lot more going faster and there's fewer going slower over there as well. So be aware that the faster a molecule is going to move, the more it's going to shift that peak to the right. And what you might see is you might see a line over on this side that might be our activation energy, right? That speed, in order for them to react, they might have to hit a certain speed in order for that reaction to occur. So let's do a question here with Maxwell-Boltzmann distribution. Say I have a distribution with number of, I'm just going to put MC for molecules, and we got speed, and we're going to want to deal with hydrogen, nitrogen, and oxygen. And I might say, draw those on the graph. Well, they're all at the same temperature, but which one is going to be moving faster? Okay, remember that smaller molecules are going to move faster. There's not as many of them. Okay, and as we get bigger, they'll move slower. So I'll just go ahead and draw my first curve, my tall peak. Which gas do you think that would be? Okay, I'm going to keep flattening it out as we go. So this first peak, the highest peak that's furthest to the left, is probably going to be our oxygen. It's the heaviest one. It's not going to have a very fast average speed. Nitrogen, which is our next one, might start to look something like this. It's a little flatter, but that average speed has moved a little bit to the right. So this would be our N2. And then something like H2 is going to look something like that. Our average speed is a lot higher. Okay, there's not as much of a peak in one spot, but the average speed has shifted more to the right. So it can be the same molecules at different temperatures showing these curves, or it could just be same temperature at different molecules traveling at different speeds here. They all have the same energy at this temperature, but their just speeds change, right? That H2 is able to move faster, but it's a lot smaller, so it doesn't put that much energy into the container. It hits that container more, though, because it is smaller and moving fast. Whereas oxygen has a little bit more weight, it can put a little bit more force against that container, but since it's moving slower, it won't hit that container quite as frequently. So that's Maxwell Boltzmann distribution. Just real quick, make sure you're able to tell how those curves will shift based on size and temperature.